All right, so we are now in lecture number 11. This is the end of the 6th week of Math 140 SCI. And we are starting, because there are no questions, we are starting on section 15.4. 15.4, the sampling distribution of X bar. The sampling distribution of X bar.
Professor, can you share your screen?
Yes, that would be a wonderful idea, wouldn't it? So let's join 2, 6, 7, join without video. Got it. Okay, share my screen. Okay, so 15.4, the sampling distribution of X bar. So as we saw last time, the population distribution and the and the sampling distribution do not always look the same. As we saw last time, the population distribution does not always look like the sampling distributions. We saw that last time, where I would make a distribution taking one at a time, which is your population distribution, and then going ahead and taking 2 at a time, or 3 at a time, or 4 at a time, or 5. And we saw that as the number went up, the shape changed. And we also happened to notice what the shape became as then got larger and larger and larger, that we're going to do that today. But the key point from last time is that the population distribution does not always look like the sampling distribution. So the question is, how does the mean and standard deviation of the sampling distribution compare with those of the population distribution? We know that every distribution has a center, has a mean, and every distribution has a spread, has a standard deviation. And the question is, how does the sampling one compare with the regular one? And to illustrate that, I want to go back to that applet again. I'm going to load it up here. Central limit here, applet. And let's share. So we're going to look at a different feature of this today, but the same one. And we're going to start with number 5, which is what kind of curve is this?
Bell curve.
It's a bell curve. So if I take one at a time, then I get a bell curve I get a curve that looks like this. Does that match what it should be based upon the shape of the of number 5? It's pretty close, right? Remember, this is actual data, which means sometimes you might get more or less than you expect, but for the most part, it's the actual shape. Now, which values are the most likely for a shape like this? 0 to 100, that looks like a bell curve. Which values, which numbers are more likely than the rest, approximately at least? Do I expect to get 0 and 100 more than the rest? Which numbers? So someone said values in the middle. All right, values in the middle. And in fact, the mean of this data is actually exactly 50.0, which is nice. It's halfway between 0 and 100. It's what I expect. Do I expect to get exactly 50.0 every time? No, but I did this time. If I do it again, we're again getting 50.0. And again, and again, and again, and again, and again. They're all 50.0. It seems that the sample size is so large that the average is right where I expect. But take a look at the standard deviation, 18.5. Remember what that means. If I go from the center, where's the center here? Which is, let's do the following. Let's make a curve. Is that a good curve? That's a horrible curve. Hold on. I'll try that again. So let's make this curve. Okay. So the center, I'm using red. That's a horrible idea. One more time. OMG. Okay, that's my curve. The mean is right here in the mean is right here in the center, give or take. And where is the, how do I know how big the standard deviation is? Remember, I go sideways until about the point where it switches from being like a bowl to a hill, correct? In either direction. So does this look like it's about 16.5 from here to there? Does that look like about 16.5 or sorry, 18.5? Ballpark? Give or take? Not horrible, right? Okay, yes. Is anyone here to acknowledge my existence? Yes, okay. So let's see what happens when I do 2 at a time instead of 1 at a time. First, let's clear this. I want you to focus on 2 things as we pay attention to this. Where the mean is and what the standard deviation is. Look at this, okay. So let's do it again. What do you notice? How's the mean and how's the standard deviation when I do 2 at a time? Anyone? So mean is the same. And what happened to the standard deviation? It got smaller. Well, let's go to 3. What do you notice about the mean and the standard deviation now? So what decreased? Because I asked for 2. Okay, the mean continued to be the same, but the standard deviation got smaller. Let's go to 4. How about now? We go to 5. How about we go to 6? What's happening to the mean and what's happening to the standard deviation as my sample size keeps going up? The SD keeps decreasing and the mean stays the same. The SD gets smaller, the SD gets smaller, the SD gets smaller, same. Okay, everything was great. And this is the point. The point is that as the sample size goes up, the mean doesn't change, but the standard deviation does. So, point one, the mean of the X bar distribution is the same as the mean of the X distribution, the original data. However, the standard deviation of the X bar distribution keeps getting smaller as n gets larger. Right? So those are the properties that we saw based upon that applet. Do we agree with that? And let's think about why this should be the case, because it actually makes sense. If you go out into the world and you measure somebody's height at random, is there a possibility that the person you measure will be 6.5 feet tall? Is there a possibility that you randomly pick someone 6.5 feet tall? Sure. Let's say you go out and you randomly measure 10 people and you average their results. Is there a possibility that the average of 10 people will be 6.5 feet tall? Sure, it's possible. How likely is it that the average of 10 random people is 6.5 feet versus finding one person who's 6.5 feet? Which one of those is more likely? Finding a single person 6.5 feet tall, or finding 10 people randomly whose average is 6.5 feet tall? It's much more likely that you find a single person, because when you take averages tend to be close to what you expect the value to be. That's why you do multiple trials of an experiment, because when you average them, the result of the average is more likely to be what you expect, because it's very tough for an average to be far away from what you expect. But for one, it's a lot more likely. So we'll say it in symbols like this, and we'll give a formula for it. If mu is the mean of the X distribution, then mu is the mean of the X bar distribution. In other words, the mean does not change. However, if sigma is the standard deviation of the X distribution, then sigma divided by the square root of n is the standard deviation of the X bar distribution. And I say this with no proof. I say this just as a fact. The distribution of the the standard deviation of the X bar distribution is the original standard deviation divided by the square root of the sample size. So if we go back to that applet, so let's go back to 1. If I do 1, according to this, what is my standard deviation? What does it say on it? What is the standard deviation. It says it right there. It's, oh, love it. 7 responses right off the bat. 8, love it. I love the participations. 18.4. If I change it so that I take samples of size 2, what does the formula predict the new standard deviation would be? The formula I just gave you. If I raise the sample size to 2 at a time instead of 1 at a time, then what does the math give me for my standard deviation? And just so you know, I used a calculator. So 13, I got 13.01, etc. Let's see what it gives me. Oh, I didn't increase the sample size. No wonder. Okay. Does that look like it's correct? And then what if I go to samples of size 3? What should be the standard deviation for a sample size of 3? $10.62. Let's see what I get here. 10.6. So, and again, they're not using theory to compute this. They're not saying, oh, the deviation should be 10.6. So let's pick numbers to make sure it's 10.6. They're just randomly generating data. And as they randomly generate data, it just so happens the deviation is 10.6 to match the equation that I provided. Again, not proving why this equation is true, just stating it as fact. Okay, any questions on that so far? Okay, so now definition. Definition. An unbiased estimator. An unbiased estimator is a statistic. Remember what a statistic is? A statistic is any number that comes from a sample. We did that last time. An unbiased estimator is a statistic used to estimate a parameter. That's what an estimator is, by the way. It's something that is used to estimate a parameter. It's a statistic used to estimate a parameter where the mean of the statistics distribution is the same as the mean of the underlying population. So, in our example, is X bar an unbiased estimator? Is our X bar? Yes, it is, because the mean of the X bar distribution is equal to the mean of the original distribution. So X bar is an unbiased estimator. Now, section 15.5 is on the other part of the applet, the central limit theorem. And just to refresh your memory, again, let's go back to that applet. And let's pick a different shape than normal. Give me something that's not normal, as far from normal as you can see amongst these 8 distributions. Which one is decidedly not bell curved? So I have some votes here for 3 and 3. Okay, so let's go 3. First, let's draw 1. Okay, let's write down the mean and standard deviation for this one. So for applet shape number 3, when n equals 1, I'm going to make a table here. When n equals 1, so it's the 3-column table. The first column will be n, the second will be x bar, and the second one will be sigma x bar, or just mean and deviation. When n is 1, I got 44.2 and 34.4. Now, according to the theorem that I gave you, if I take a sample of size 2, what should be the new standard deviation and what should be the new mean? What should be the new standard deviation and what should be the new mean? And you're all more than welcome. You can talk out loud. You can type it. You can even dare to put yourself on camera. So I have a 24.3 for which one? The mean or the deviation? N equals 2. We're going to go to sample size 2. So I have 24.3 for the standard deviation. What about the mean? What should that be? Mean should be 44.2 still. Well, let's take a look. Let's go to sample size 2 and let's do it. Weird shape. What's the mean? A 44.1. That's basically the same thing. And what's the deviation? $24.3. All right, now this is a very weird looking shape, huh? Let's go to sample size 3. What should the mean be and what should the deviation be for this one? What should be the mean and deviation for a sample of size 3? Anyone? So I have 14.02. What should be 14.02? Oh, I see what you did. No, you have to go back to the original one. You can't use 2 to get 3. You have to use the original one to get 3. So you don't do 24.3 divided by the square root of 3. You do the original 34.4 divided by the square root of 3. Because remember, we're always comparing it to the original distribution. And I get 19, I got 19.86, but maybe I just use more decimals than you. But let's see what it says for sample of size 3. It gives me 44.1 again, and this time 19.8. Which is still ballpark what we expect, correct? And if I go back to the beginning and I do sample size 4, what I expect? And by the way, don't only focus on the mean and deviation, because also focus on the shape. Does this shape look like anything important? 68.8. Flower, 68.8. How do you get that one?
You said comparing back to 34.4
Yes.
times divided by the square root of 4.
Yes.
Maybe, oh wait, I think I did it wrong.
I think so as well. So yes, 17.2. Let's graph that. Hey, look at that. Exactly what the math tells us it should be. So what's happening to the mean? It's not changing. What's happening to the deviation? It's going down as expected in exactly the right way that we expect. But let's now look at the shape. Does this shape look like anything to you? I mean, not yet. If we go to 5, if we go to 6, okay, by now by 6 it looks like, yeah, it's kind of getting there. Kind of getting there. 7, 8, oh, by 8, already by 8, it's like, oh yeah, that's a nice bell curve. 10, 13, 17, look at that, right? How high can I go? 20, 30. Okay, by the time I reach 30, right? Beautiful. Even by 8, it was already looking like a bell curve. So this is the idea of the central limit theorem. The central limit theorem says as follows. Right? The central limit theorem says, draw an SRS of size n from any population with mean mu and standard deviation sigma. When n is large, the X bar distribution is approximately normal with mean mu and standard deviation sigma over the square root of n. If the underlying population was already normal, then X bar is normal. So in general, it's approximately normal, but if I start normal, I stay normal. What's an SRS? Did we do that? A simple random sample? When we talked about the different ways of sampling, we talked about an SRS, a simple random sample. Remember that, Cynthia? I think that was you who asked, right?
Oh yeah, I just got confused because like you abbreviated, so like
No problem, no
I
problem.
didn't know what it meant.
No problem. Yeah. Always ask. No problem there. Always ask. Okay, so this is the central limit theorem. So
Could
I
you
would
go-
let, huh?
Could you go a little bit higher so I could see the top chart, just so I could copy it really quickly?
Oh, those are just the numbers that we did, but yeah, of course. Tell me when you're ready, please.
Thank you.
All right, so let's do an example. The last few chapters have been lots of definitions, but no, not a lot of examples. So now that we have some theorems under our belt, let's go ahead and do that. So here's the following example. It says the time in hours that a technician requires to perform preventive maintenance on an air conditioning unit is governed by an exponential distribution, which you don't have to worry about, whose density curve appears in 15.6a. So I'm looking in the book, and you have a curve that looks like this. This is my density curve. Okay. This is what an exponential distribution looks like. It's very high on the left and it drops off on the right. It extends to infinity. It keeps going, doesn't ever hit the x-axis and stop. It goes forever. It's asymptotic. It goes forever. It just gets smaller and smaller and smaller and smaller and smaller the further we go. Okay. So what is it saying? It's saying most of the time when a technician is working on a job, it ends very quickly, a small amount of time. And if it takes a lot of time, that's very rare, much more rare if it takes a lot of time down the line. Right? Does that make sense what this thing looks like? This is time, how long it takes, and the y-axis is, of course, probability is area under a curve is percentage. So we don't really label the y-axis as long as we understand that the area under the curve has to be 1. It's got to be somewhere, right? Remember the 2 rules for a distribution? It can't be negative, and the area under it has to be equal to 1, right? Those 2 things, because we have to get some result. So if I add up all results, it has to add to 100%. Area has to be 1, and it can't be beneath because that would imply a negative likelihood, which does not make any sense. Okay, so the y-axis is essentially probability. It's how likely is it to occur. Why does it look different than the graph we had earlier with a straight line? Which graph did we have earlier with a straight line?
It was like a regular graph, and then it was a line drawn and the area had to be 1.
So you're talking about this one. You're talking about number 1, right?
Yeah.
Number 1, this distribution represents a scenario where everything is equally likely, where the number 0, the number 12, the number 18, 36, 72.5, and 100 are all equally likely. So we expect a situation accounts where every number occurs roughly the same number of times. But not everything in life is like that. If you look at heights, is every height equally likely? Is it just as likely to find someone 6'5" as it is to find someone 5'7"?
No.
No, heights look more like 5, where most people are in the middle and it kind of tapers off to either side. Our distribution is like number 8. It's very likely to get small results and very unlikely to get large results, right? Think of a technician, like our example is, a technician working on a job. Most jobs are easy to fix. They're minor fixes. Oh, just hit this button. You got to turn this knob. Oh, didn't turn the power on. Every now and again, you get a job that takes a long time. But if they all took a long time, nothing would ever get accomplished, right? So most jobs are easy fixes, and some jobs take a longer time. So in our particular example, we have this technician performing a job, and the time it takes to finish is modeled by a shape that looks like this. Lots of times it's over quickly, and the longer it takes, the less likely it is to take that long in the first place. Does that make sense? Okay. It says the exponential distribution arises in many engineering and industrial problems, such as time until failure of a machine or time until a success. Exponential distributions are, in fact, one of the most important types of distributions that are out there. The normal curve is obviously the most important. The bell curve is the most important. The exponential distribution is not far behind. Okay, it's an extremely important shape. And just so happens to be the one that we're working with on this problem. Okay, so let's see where we're going with this. The mean time, mu, is equal to 1 hour. So data suggests that the mean for this example is 1 hour, with a standard deviation is also 1 hour. Okay, and just so you know, It is a distinguishing feature of the exponential distribution that the mean and standard deviation happen to be equal. Usually this is not the case, but it happens to be the case for an exponential. Which is fine. That's just numbers. The fact that they're equal is irrelevant for this problem. They just happen to be equal. Your company has a contract to maintain 70 of these units in a building. Okay, so you own a building or somebody owns a building and they say, hey, we have 70 air conditioners and it's your job to make sure that these air conditioners are running correct. So 70 units and equals 70. There are 70 units. Now, each unit on average takes me how long? How long to fit each one on average? One hour. That's exactly what the mean means. Now, do they all take exactly 1 hour? Is that realistic? No, some take less time, some take more time. So your company has a contract to maintain 70 of these units. Is it safe? Is it safe to budget 1.1 hours per unit? In other words, if I say, okay, I want you to come out and check them all, and you say, okay, on average, each one should take 1 hour. So I'm going to give myself 1.1 hours for each unit and however many hours it takes. Or should you budget 1.25 hours per unit? That's the question. Is it safe to budget 1.1 hours per unit, or should I budget 1.25 hours? Now, this is important ramifications from a business perspective. If I budget 1.1 hours, but there's a high likelihood it's going to take longer than that, I can't get to them all. Some of them might fail. I might be out money later on. If I budget 1.25 hours for each one, I might finish the job way early, and now I'm paying my workers to sit around doing nothing because they got nothing to do. Right? So the question is, how much time should I budget? So the question is, what is the probability that it will take more than 1.1 hour per unit? If there's a 50% chance it'll take more than 1.1 hours, should I budget more time? What do you guys think? If it's 50-50 that it'll take more than 1.1 hours per unit, should I budget more time? Yes. If it's 10% chance it'll take more than 1.1 hours, should I budget more time? Probably not. Probably not. 50%, yes. 10%, probably not. Even 20%, you might say, yeah, 1 in 5. Do I really want to spend? Do I really think? I mean, these are the questions of the business, as a business owner, you have to decide. But what we're looking for is, what is the likelihood that it's going to take more than 1.1 hours per unit? Now, when I look at this shape, this is not a normal curve. This is not a bell curve, right? It's not a bell curve. So how do I use what I've learned so far in a situation where it's not a bell curve? Because all the math that I've learned in terms of probabilities using my calculator or tables or crunch its programs that you find on the internet, they only work for normal curves. We don't know any way of doing it with it for other stuff. By the way, you can do it for other stuff. It just requires some calculus. I mean, how many times so far have I said, oh, just you got to know some calculus? Okay, calculus can do some amazing things. And it really allows us significant flexibility in what we can accomplish. Okay, but the point is, how can I do it without calculus? And the answer is, if only I could replace the original shape with a bell curve. Because if I can replace it with a bell curve, I have the tools to do that. Am I allowed to replace it with a bell curve? And the answer is yes, because of the central limit theorem. When n is large, the X bar distribution is approximately normal. How large is large? Well, I mean, we're going to 70, but let's look at what happened here when I went up to 5. Already by 5, it's looking normal, right? If we did 3, well, let's go in order. So 1, certainly not normal. 2, not normal. 3, still got a tail on the right side. 4, a small tail. 5, very minor tail. By the time I reach 10, tail's almost completely gone. 15, slight, if anything. I mean, these are all in the ballpark of normality. And I can only go up to 30. We're going to 70. So by the time we reach 70, we can certainly use normality. We can certainly use the normal curve. So let's see how to go ahead and do that. Since we're looking for averages, I don't care about these numbers. That's for 1. This is for X. This is for the underlying population. I want the mean for X bar. I'm going to call this sigma X and mu X and sigma X. I want to know what is the mean of my X bar, of my average, and what is the mean of my, and what is this deviation of my average? So what is the mean of the X bar distribution if the mean of the underlying distribution is 1 hour? One. Because what we saw before is they are the same. And what is the deviation of my underlying distribution if the sigma of the original is 1 hour? What is the underlying 0.12 hours? Do you all see that? Yes, no, maybe so. Anyone not sure where that came from? I could add a line here. It's equal to 1 over the square root of 70. You take the distribution, sorry, you take the deviation of the original and divide by the square root of the sample size. So we get 1 hour for the mean and 0.12 hours for sigma. And now we're curious, what's the probability that X bar, that the average is greater than 1.1? This is what we want to calculate. What is the likelihood that the average is greater than 1.1? I don't care about X being greater than 1.1. That's 1 at a time. I want the average of 70. I want to know the likelihood that that's bigger than 1.1. Well, how do I compute this? How do I compute the probability that the average is greater than 1.1? And just so you know, there's multiple ways, so I'm accepting any of them. One of them is by z-scores. You can compute the z-scores. Let's do it that way too. If I compute this to a z-score, how do I compute this to a z-score? By replacing 1.1 with what? First formulaically, and then we'll do the math. What do I replace 1.1 with if I want to do a z-score approach? .8643. Tell me how you got that, please. I'm not saying it's wrong. I haven't done the math. I just want to know how you computed that. The table. I'm not ready for the table until I know my z-score. I can't compute my z-score. I don't even go to the table. I think you looked for 1.1 in the table. But I can't go to my table yet. I can't go to my table until I have a z. So I got to first compute the z. How do I get the z-score of 1.1? Who recalls the formula for that?
Is it x minus u over a standard deviation?
Yes. Use the equation x minus the mean over the standard deviation. So 1.1 minus 1, well, that's not that hard. Divided by the deviation. Oh, wait a second, Flower. So you got, I don't know how you got, oh no, that's still a little off. Okay. So equal to the probability that z is greater than 0.837. Did you all get 0.837? So now, how do I compute the probability that z is greater than 0.837? You have multiple methods. One, of course, is the table. But we also have our calculators. In fact, if you were going to use the calculators, I could have done it from the start. I don't have to go to z. But either way, go ahead. I don't have my calculator with me because I left it somewhere. I got to find it. Until I do, what is the probability? I have the answer here from the book. What is the probability that z is greater than 0.837? Approximately.
For the, do we look on the Z table for like with the 0.837?
You can certainly use the z table, and you're looking for 0.837, or I guess in your table it would just be 0.84, because I don't think your table can do 3 decimals. But you could also use your calculator. Your calculator, 0.837 is a lower limit because it's greater than 0.837. So 0.837 is a lower limit. What's the upper limit? $9,999,999, very big number. What mean and deviation are you going to use? Ooh, excuse me. What mean and deviation? So that's not correct. If you're going to use, it's still not correct. If you're going to use 1 and 0.2, then you are using the original data. You're not using the new data. You're still in the original, which is fine. In that case, your lower would not be 0.837. Your lower will be what? If you use the original data, what's your lower going to be? 1.1, because it's 1.1 and above. If you switch to a z, then the mean and deviation are always the same 2 numbers. Now, equal to each other, but the same too. The mean is always this, the deviation is always that. What are the mean and deviation for Z? Recall. What is the mean for Z and what is the deviation for Z? Nothing to do with this problem. These are universal. 0 and 1. If you're going to use Z and you want to convert to Z scores, which again is totally fine, then you have to remember that the mean and deviation are going to be 0 and 1. If you want to use the original data, which is also fine, then the mean and deviation are 1 and 0.12. So what do you get? In this case, what is the probability that Z is greater than 0.837? What does our calculator give us?
Do you actually do it on the calculator? I forgot how to do it on the calculator.
I can walk you through it. You're going to hit second vars. And you're going to go to normal CDF. And you're going to put a lower 0.837, upper 999999999, mu 0, sigma 1, and compute. So what do you get? Anyone?
0.2012.
So yeah, so the book gives you 0.203. Again, at that point, you're approximating at the 1,000th place, so don't worry about it. If you got 0.201, 0.203, same thing. But that tells you that there's a 20% chance that on average, it will take more than 1.1 hours per unit. If you are the owner of this company, can I explain it for a TI-83? No, because I don't have a TI-83. I know it's similar, but I don't know the details. So especially if it's not in front of me. So what I would recommend is just do a YouTube search. How to use a TI-83 to compute probabilities for a normal curve. And it should walk you through it. I'm sure there's a million videos on the subject, but I can't see it offhand. Hope that's okay. Should using X bar or Z in the formula give different answer? Well, you're not actually using X bar or Z in the math, right? X bar or Z are our symbols. But if I want to use X bar, it has to be these three numbers. And if I want to use Z, it has to be these three numbers. And other than an approximation difference, you should get the same results.
Okay, thank you.
Okay. So the question again is, should I budget 1.1 hours per unit or should I budget 1.25 hours per unit? What does the math tell us? 20% chance of it occurring. Would you be comfortable with that likelihood? If I put a gun to your head and said, I'll give you $1 million. There's a 20% chance that the bullet will kill you. Would you take the chance? For $1 million, any Squid Game fanatics here? Would you take the chance? No. No, I know I wouldn't. Maybe for $1 billion, but not $1 million. It's not enough. So the question then becomes, okay. If I go to 1.25 hours per unit, what's the likelihood I'm going to need more than 1.25 hours then? All I got to do now is do the same math, but instead of using 1.1, replace it with 1.25. If I do that, what do I get? Probability that X bar is greater than 1.25 is equal to what? Let's use our calculator for that. Let's not go Z-scores. Let's just go directly to the calculator. What's the probability that X bar is greater than 1.25? What does the calculator give us? Let's see. Can I do it on this calculator? No. Must be away. 0. No. 1.12. 1.25. I think it was this one. Is that it? No, I don't think so. Okay, what do you guys get? I don't think my calculator knows how to do this one. Anybody? What is 0.281? 0.281, that's a higher probability. That doesn't make any sense. It can't be.
I got 0.5773, but
Wait, point what? But what's like? Let's think about what we're saying here. If I graph the X bar distribution, whose mean in the center is 1, and whose deviation is 0.12, then when I go out to 1.1, which is about here, I'm going to get a certain value, and that value was 20.3%. And now we're saying, okay, if you don't go to 1.1, but you go to 1.25, which is out here, now we're looking for that. So if you're getting a percentage greater than 20.3, that doesn't make any sense, because you can just tell by looking it has to be less. Right? Do we agree with that? Anyone? Hello? Is anyone following me? Anyone? Oh, some yeses. Hopefully that was what I just said. I'm trying to do it on this calculator. Oh, okay, I think that's the right button. So 1.12 and 1.25. No, that can't be the right button. All right, so what's everyone getting? Is anyone doing this? Is anyone with me? I get 0.019. That makes more sense. I don't think anyone said that. Did anyone say that? Oh, Mary, I saw. Oh, I see a few people wrote that. I just didn't see that. I'm so sorry. So Luis and Mary, I'm sorry. I didn't see that above. So I don't have my calculator working, but the book says about 2%. So 0.019 seems to be about 2%. Would you be comfortable as the boss allotting 1.25 hours per unit if there's only a 2% chance that it takes longer? Yeah. Okay, so 20% chance, probably not. 2% chance, probably yes. Obviously, if more depended upon it, you might adjust your boundaries, not for mathematical reasons, but for just practical reasons. That's on you. But in general, this is the idea of a sampling distribution. Does this make sense? Are there any questions on this? Yes, no, maybe so. All
could
right.
you actually walk through the calculator for that second one we did?
Oh, the second one, I just went ahead back to my calculator and I plugged in 1 hour for the mean, 0.12 hours for sigma, 1.25 is my lower limit, 9999999 for my upper limits, and hit calculate. Yes, no, maybe so.
Sorry, you said that kind of fast. Can you repeat that real quickly?
Sure. Put in 1 for sigma, 0.12, sorry, 1 for mu, 0.12 for sigma, lower limit 1.25, Upper limit 9999999 or something like that. It's the exact same way we did the other one. We just changed one number.
Okay, thank you.
Does that make sense?
Yes.
Okay, and you should get the same thing we did, which I hope you did. Okay. So that takes us to the end of 15.5. And now we move on to section 15.6 on sampling distributions, which we just covered. Sampling distributions and statistical significance. Statistical significance. I think I spoke about statistical significance last time, did I not? Pretty sure I did, or maybe even 2 times ago. Right, statistical significance is when you get a result that should not have occurred by chance. But it did happen. And you're like, what? That's crazy. That shouldn't have happened. So you conclude that there must have been some kind of design behind it, whether someone cheated or it's weighted or this or that, or my assumptions were wrong. You know, if I believe, for example, that the average height in America is 6 feet, I believe the average height in America is 6 feet. I go take a sample of 1,000 people and I get 5'7". 1,000 people is a pretty large sample. So the result of 1,000 people being 5'7", I got to start asking myself, wait a second, is that just a really rare occurrence, but I was right all along? It's really 6 feet? Or do I say maybe my assumptions about it being 6 feet were incorrect? So what we're going to be doing as the semester progresses is all about, are my assumptions correct based upon the results of my experiment? Or is it just a rare fluke? For one person being 5'7", okay, I got a short person, that happens. For 1,000 people to get a result of 5'7", I got to start saying 6 feet is most likely not actually correct. Okay, so statistically significant results are the results that make us question what we've been assuming up until now. So let's do an example from 15.6. It says we have an SRS. That's a simple random sample of n equals 1,000. N equals 10. And it's a normal population with a mean mu of 25 and a standard deviation of 7. So I took an SRS of size 10 from a normal population whose mean was 25 and sigma was 7. I did this 1,000 times. So I took 1,000 samples of size 10 each. And I care about the averages, right? The goal is, what is the average of my sample? So what is the mean of my sample? What is my sample average? Or the mean of my sampling distribution in this case? 25. And what is the standard deviation of my sample average? Not 7. 7 was a deviation of my population. That's one at a time. I'm not taking them one at a time. I'm taking them how many at a time? 1,000 at a time. No, not 1,000, I'm sorry. I do it 1,000 times, but I don't take them 1,000 at a time. I take them 10 at a time, right? That's the n equals 10. I might have done this 1,000 times, but I take them 10 at a time. My samples are size 10. So my sigma is not 7, but rather 2.2. Okay, I did this 1,000 times. Did what? Took a sample of size 10. So here's a sample of size 10. Here's a sample of size 10. There's a sample of size 10. There's a sample of size 10. How do I get 2.2? Cynthia, you want to explain? How do I get 2.2?
So you use the standard deviation divided by the square root of n. In
And
this
what-
case, the standard deviation is 7, I'm sorry.
Right?
So you do standard deviation 7 divided by the square root of 10.
Excellent, right? 7 divided by the square root of 10, 10 being the sample size. I took 1,000 samples, but each one was size 10. Luis, does that make sense? Okay. And my results, I'm going to load up the ebook here so I can show you the results because I don't want to copy this. It will take forever. And we are in chapter 15 and 15.6. So the results are as follows. Okay, so here's what happens. Again, I took 1,000 samples of size 10. Okay. In their case, they took the medians of their samples, but I took the averages. That's not what I want to focus on. Okay. But I took 1,000 samples. Well, that's at size 5. Oh, okay. So my bad. 1 second. 15.5. They reference 1 second. It says here in example 15.5. So where's example 15.5? That was actually in section 15.4. Okay, here we go. So in example 15.5, okay, here's example 15.5. Okay, we have a situation where the mean is 25, standard deviation is 7. We take lots of SRSs of size 10. In our case, we took 1,000 SRSs of size 10. What do we see that the sigma was? It was 2.2 approximately, if you want to be a little more exact, 2.2136. Let's look at the original population distribution and then our sampling distribution. You'll notice that the sampling distribution is much skinnier, correct? Because remember what sigma is. It's how far you go from the center to where it changes from a bowl to a hill. If the sigma is smaller, you're not going to move out as far for that change to occur. So it's going to be much tighter. Agreed? But of course, the area under the curve has to be 1 though. So if it gets skinnier, how can we keep the area 1? It has to get taller. The only way for the area to be maintained at 1, if it gets skinnier, is for it to get taller. Luckily, the tallness, we don't care about in this course, other than the fact that it exists. We care about one spot being taller than another spot, because that means it's more likely over there than over there. But the actual height, we don't care about. So this is the original. Okay, very spread out in comparison. And as our samples, as our sample size gets larger, we expect it to get a lot skinnier. Okay. They don't actually show what I thought they would show, which is kind of weird. It says page 351, but I don't see one on page 351. Figure 15.3. I guess this histogram, they kind of smoothed out the histogram. In other words, it's imagine there's like these columns here to make a histogram, and they smoothed it out. But it's behind the scenes going on. I don't really like how they did that. In our example, in 15.6, on the other hand, section 15.6, okay, we have the same situation. This is a samples of size 5, not samples of size 10, but rather samples of size 5. And we didn't actually graph the mean, we graphed the medians. So we took 5 at a time, computed the median. And we did that 1,000 times. Notice that the median is also centered at 25. Do you see that? Look at the center of this, right? Where's the median of this? Yes, no, maybe so. Okay, the mean, so the mean of the sample was 25. But here, for the same case, we actually made a histogram of the variances, which is the square of the deviations. So again, we took these samples, we computed their deviations, each small sample of size 5. We squared it, we got the variances. Does this look like it's normal? Does this shape look like it's normal? It's peaked, but it's got a long tail on the right side. Okay, it is not normal. It's actually, although I don't see it here listed, we'll get to this later in the course. Anyone know the shape of this distribution where it peaks and then has a long tail on the right side? Anyone happen to ever do stats and might know it? It is called a chi-square distribution. A chi, someone said in chat, someone said it is skewed right. 100% is skewed right. But it has a specific name. It's called a chi-squared distribution. We will get to that later in the course. We're going to need it near the end of the course, the chi-square. On the next page, we do the same thing, but this time we do the standard deviations. Not the variances, but the standard deviations. What do you notice about the shape of the distribution curve when we look at the standard deviations versus the variances? It's also skewed to the right, not as much because we took the square root, so the numbers are smaller, but it is still somewhat skewed to the right. So the variances and deviations, if we did a histogram of those are not normal. But the mean by the central limit theorem is normal. So don't just assume that anything is going to be normal if the sample size is large enough. It's only if it's normal. Sorry, if it's only the mean that the central limit claims is approximately normal. So I want to write that down as a very important point right here. Okay, so note from graphs in book, the mean has a normal distribution when n is large, but sigma and sigma squared do not necessarily have the same property. Don't try to apply this to anything but the mean. Okay, so far so good. Questions, anything we've done so far? Yes, no, maybe so. Hopefully. A result is statistically significant. Just to rewrite it. If the probability of its occurrence is so small that it would rarely occur by chance. A result is statistically significant if the probability of its occurrence is so small that it would rarely occur by chance. So if something is so rare and it occurred nevertheless, we say it is a statistically significant result. We question whether or not our assumptions are behind the situation are correct. If it's an unlikely event, but it's not rare, we might be surprised. I flipped 3 coins or 3 dice and they're all 6s. Has that ever happened to you in your life? You ever flip 3 dice and get all 6s or all the same number? You don't expect it to happen. You're a little surprised when it happens, but it's not so rare that you start to question whether the dice are fair or not. Right? A statistically significant result makes us question our assumptions because this shouldn't have happened. And yet it did happen. So something must be wrong here. Okay? So this takes us to the end of chapter 15. The central limit theorem is by far the most important feature in chapter 15. So as you go through the homework, you will have questions on the central limit theorem. Okay, it is the key. It's one of the big ones. Starting next time, we're going to start on confidence intervals and hypothesis testing. This is where it gets fun. So be ready for lots of fun. And when I say that, I mean more fun than it's already been because it's all math and we know it's all fun. Okay? Yay, that's what I'm talking about.